that term disappears. When that term disappears, you get back to this equation here. So we've said, let's make this circuit simple. Let's imagine the capacitor has initially got no charge on it. That means that Vc at time t equals 0 is 0. And so this equation reverts to this one here. And now what we want to do is reorganize it. So we want to find out that actually Vc does this. We want to know that Vc does that. The only way we can do that is to get Vc of s on its own, get that Vc of s on one side of the equation, and then inverse the Laplace transform. So we mush this equation around. What we do is we take terms from one side to the other side, divide whatever we need to do to get Vc of s on one side of the equation, and that's what we've done by going to here. So when we reorganize that equation, we get Vc of s is I of s over Cs, and we've said that I is a constant, so I of s is I naught over s, where I naught is the value of the current. And if you then simplify that expression, you get I naught over s squared c, and so now you've got this equation here, this big equation here, where on one side you've got Vc of s, and on the other side you've got I naught over s squared c. And now you inverse the Laplace transform. Let's inverse the Laplace transform, and if you inverse the Laplace transform, using your Laplace transform tables, which are these things here, a copy of which you will have in the exam, inverse the Laplace transform, you get this. And believe it or not, what this is saying is, you could plot it like this here. That is Vc equals I naught over c times t. That is the expression for that line, like that. Right, I've now got a question for you. I'm going to do this. In fact, I'm going to not do it on that, because you might want to keep that. I'm going to do it on here. Ready? That's the C, that's the VC, this is IC. So we've got that. VC, T. Now what happens?
It's going to go negative. Wouldn't if it's negative, I only count as a negative after the cycle or something?
There's no cycles going on here. There's no cycles, it's a constant current. There's no cycles going on.
Changes the estimate.
What have I changed? What have I changed?
It's a negative current rather than
Yeah,
positive.
it's got negative current. Current's flowing in the opposite direction. So, discharging. What does the word discharge mean? Yes. Is that voltage going to approach zero when it starts off at zero?
No. It's already at zero.
It's already at zero. So it's not going to be discharging. Is it going to be negatively charging? It's certainly going to be charging. No doubt about that. It starts off with 0 volts across it. It's definitely going to be charging. Is the voltage going to be getting bigger? Or is it going to be getting smaller?
It's going to be bigger, but in a negative.
He says smaller. What do you say, Phil?
Bigger, but negative.
Bigger. The voltage is going to be
Bigger.
bigger in magnitude.
Big magnitude, yeah.
It's a matter of words, isn't it? Is -3 bigger than -2?
No.
It's up to how you...
Is -5 bigger than -2? Sorry?
Mathematically small.
It's smaller, isn't it? Yeah. Smaller. The voltage is getting bigger. Isn't it? It's already at 0. Okay, well let's have a look at what happens. Will it do this?
Depends on
What will it do? Will the gradient be positive or negative?
Negative.
A negative gradient. Will it do this then?
No, it'll be positive gradient.
Starts at 0. Will it do this then?
Yeah.
Who said yes? Put your hand up to see. Yes, it does do that. It does do that. And we know it's a negative gradient. And the reason why we know it's a negative gradient is because IC equals C dVc by dt. We know that. And we know that IC there, this current here, IC, is minus I naught. And what that equation is telling us, is that this gradient here has to be negative. You can't have a negative capacitance. Capacitance is always positive of a value. So the only thing on the right hand side of this equation that can be negative is dVc by dt. That's the only thing that can be negative. So what that means is this VC versus time graph over here must have a negative gradient. It must have a negative gradient. And the voltage across the capacitor is getting more negative like this. It's moving in this direction like that.
Can you zoom out more?
Yeah.
Just in general.
It's going to be doing that. Do you know before, on this expression here, I said that this capacitor voltage here was equal to I naught over C times T. Can you see that? Yeah. What I want you to do is I want you to tell me what this capacitance equation is here. What's this one here? I want you to do the maths. Do you want me to leave this up so that you can do it from here and copy some of it or look at it? Or shall I take this away? Shall I take it away or shall I leave it here? Say again? Yeah. I'm surprised you haven't done the past exam papers by now. Started them. You need to go to the office and ask them to do it. They do it because they our school office. They put them up. They do it because Oh, yeah. Show me something. Yeah.
I just did my maths to the other situations that we had.
Yeah. You can do it that way, but you've got to show all the mathematical steps, which means you've got to include the constant of integration. I've included the constant of integration. Whenever you integrate something, you get a constant. And then you've got to use also on that constant instead of that constant. I can see you have, but I'm just asking.
No, I haven't.
No, well, there we go. Yeah. So I want you to go through the maths undo that.
But no, I haven't integrated it yet, so technically I don't know.
I want you to go through the maths to get this out. So I want you to do
C plus C like that.
I want you to go through the maths yourself. I want you to go through the maths and get that equation out.
It's just going to have a negative, I think, isn't it?
No, I know, because he's saying no initial condition, so I could define that in. Oh, yeah, but I was wondering.
That's always going to be, isn't it? Same thing as the negative sign.
Can I ask a question? Our scheduled timetable for this slot is 2 till 4. I've seen it on the schedule that we've got. Is there any reason why we can't make it 1 to 3?
That's right.
Say again?
Supervisor meetings is a bit of a funny one for some of us because Simon's only available until 2 o'clock on a Tuesday. So, I mean, that's the only reason I've got, really.
Can you see Simon another time?
I can see it on Friday, yeah.
Could you do that so that we can start early on the Tuesday and start at 1?
We could do 1 till 4.
We can do 1 till 4 if you like.
Senior test papers, so I wouldn't mind.
You can see my exam papers.
I thought it looked good.
They look quite hard.
Yeah, I looked like
Than this. Yeah, but we've got a whole second semester to get to the point where we can do those. We've got a long time yet. Yeah. You're the model. Do you model, don't you? Or do you not? I mean, it's probably very. If I was going to model it, when we did second year lab, EO227, we modelled transformers and we modelled the motor. Yeah, well, you can do. Okay, so what it is you're going to come out with then, and you should have done it by now, is you should have come to the conclusion that you should have done all the maths. I'll do the math steps here for you now. You ready? Okay. I'm going to Laplace transform this equation here. And if I Laplace transform this equation, I get minus I naught over S, because that's the Laplace transform of a constant. I naught equals C. Laplace transform of dvc by dt is minus vc at time t equals 0 plus svc of S, like that. Done that step before. Now we're going to say that the voltage on the capacitor at time t equals 0 is 0, so that goes to 0, and so I naught over S equals SCVC of S, like that. And if you rearrange this expression, you get VC of S equals, and you've got to put SC below here, you get minus I naught over S squared C. And you can rewrite that as I naught over C minus I naught over C, and then multiplied by 1 over S squared, like that. Now we do the inverse Laplace transform of that step, and you get Vc as a function of time is minus I naught over C times t. Because the inverse Laplace transform of 1 upon S squared is just t. And now you can see that this expression here, Vc as a function of time, equals minus I naught over C times t. And so you can write here that Vc up here is minus I naught over C times t. And that is this graph here. That's that plot. Are we all happy with that? Oh, move it up. So, what I want you to do now then is there anybody who should be here that isn't here? Are we all here that should be here? Yeah. Okay, so next week we will start at 1 o'clock in this room and not 2 o'clock. Okay? Can you all make a note of that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 of you. All 17. I think everybody's here. All 17 are here. So you've all got the verbal message, and I'll put an announcement on Student Central as well, saying that we start at 1 o'clock, and we can, if you wish, go on till 3, if you wish. Or 4. Oh, we want to do what, sorry? No, we're going to go on till 4. I want 2 hours at a time. Are we happy with that? Can we do the next bit? Okay, let's do the next bit then. I'm not talking about next week. I'm talking about from here onwards. Yeah, from here onwards. You're quite right. It shows that we don't have a lecture next week. Okay. I want you to do this for the question now. The question in this particular case is, I'm going to write it at the top here. Can you see that? What I've written? I can't see it. I can see it now. This is really important, this. Yeah, I is constant, and it's equal to minus I naught. There we go. What do we think is going to happen this time? Someone tell me. Someone tell me what's going to happen now. Anybody know? Without guessing. Current is minus I naught, it's a constant. The voltage across the capacitor at time t equal naught is minus V naught. It's not even positive, it's negative. What does the graph look like? Yeah, tell me. Shall I draw here? Yeah? That's time along there. This is VC. Where does it start from? At time t equals 0. Yeah, it's minus V naught. It starts there. And is it going to go up? Like this? It's going to go negative, yes. Let me ask you a question. What's the equation of VC here? What's the equation of this line here? Well, you're going to write, this is VC as a function of time, that's time. So you're going to write something like VC is a function of time equals something. What would we have here?
Minus V naught.
Yeah, minus V naught. Go on.
Minus I naught minus C times T together.
That's it. Well done. We've done a current source with a resistor. We've done a current source with the capacitor. And now we're doing the current source with the two things together. Okay? So this current, when it gets round here, of course it's going to split into two, IR and IC. It's going to split into two. And I'm going to make this current constant. So I equals I naught equals constant. And the question is, of course, as always, what is VC doing? What is VC going to do? And the way we do that is we use all the fundamental equations that we know that's going around here. What's the most important equation we can write to relate these things? We want to find out what VC is doing. What's the first equation we could write down? We can write down the first equation. What would be the first equation that I would want to write down in an exam?
I equals IR plus I.
Thank you, yes. I equals IR plus IC. No one could argue with that one. We all understand that one, don't we? Yeah?
Yes.
And now what we've got to do is realise that, of course, I is a constant. This thing here is a constant. IR, is that going to be a constant? No way. There's no way is IR going to be a constant. The only way IR could be a constant is if the voltage across that resistance was a constant, because that's what we had before. We're not going to have that now. What about IC? Is IC a constant? No way is IC going to be a constant. I'll tell you why it's not going to be a constant. So look at the overhead. That's it. I want to see your eyes up there. Right, this is why it's not going to be a constant. Just look at what's going on. When we had the input current here, this supply current was a constant, we didn't have a resistor there. We had no resistor. So all that constant current was flowing into the capacitor. We had no resistance. We've got some resistance here now. So some of that current is going to flow through this resistance. And of course, as some current goes through the capacitor voltage changes, obviously, because the voltage across that capacitor changes, because that current is causing the voltage across that capacitor to change. So the voltage across the capacitor changes, then of course VR also changes. And if VR changes, the voltage across the resistor, it means the current in the resistor changes. So the current in this resistor is changing. If the current in the resistor is changing, even though you've got a constant input current, this is the input current, that's constant. If IR is changing, it means IC is changing. You got that? What do you think is going to happen? Looking at it. Input current constant to the whole circuit, this current I equals I naught, flowing through there. What's going to happen? We can do the maths, or we can do the understanding. I don't know which one you want to do first. The understanding. Okay. Well, my understanding is going to be like this. This current here, I, which is I naught, which is a constant, is not changing and is feeding these two things here. When it feeds the capacitor, the voltage across the capacitor increases. When the voltage across the capacitor increases, the voltage across the resistor increases. When the voltage across the resistor increases, the current in the resistor increases, doesn't it? Until such time as the current in the resistor steals all and takes all of I naught. All of I naught now is flowing through that resistor, and the voltage across the resistor is increased to that point where all the current I naught flows through that resistor, and no more current flows into the capacitor, and won't flow any more into the capacitor. If there's no current flowing in or out of the capacitor voltage is constant. So one thing we know sure is that the voltage across this capacitor is not going to be carrying on ramping up. Don't you agree with that? Yeah. It's not going to carry on ramping up. Not like before, where we had nothing curbing the current. Now what's happening is as the capacitor voltage increases because there's current flowing in it, the voltage across it increases, across that capacitor. The voltage across the resistor increases because they're both the same. Don't forget, VC equals VR here. So the voltage across the resistor increases. As that increases, the current in the resistor increases until it reaches a point that it's equal to I naught, and then no more current flows into the capacitor. The capacitor voltage is fixed. That's what's going to happen. Now let's do the maths. So the first thing that we can write down is that IR equals VC over R. And the reason why it's VC over R is because VC equals VR. So you could say that VC over R equals IR, which equals, VR over R. VR, you see that VR down there, left-hand side? VR over R equals IR. And because VR equals VC, that's VC over R. Have we got that? And we can also write that IC equals C dVC by dt, just like before. So those equations still apply. And now what we've got to do, of course, is pop these in. Pop this into there, pop that into there, and so you can write that I equals VC over R plus C dVC by dt. Now, when you get an equation like that, what do you call it? When you get an equation like this, what is it called? What's this equation called? What form? First order differential equation. It's a first order differential equation. Now you know why we have to use Laplace transforms. It's because if you want to solve first, second, third, any order differential equation, you've got to use Laplace transforms. Don't use integration and do things like that. You just make a headache for yourself. If you use Laplace transforms, it becomes easier. So we're going to use Laplace transforms. So what we've got to do is make our substitutions, and we're going to say, right, let's Laplace transform this equation here first. If you Laplace transform that equation, you get I of S equals VC of S over R plus C minus VC at time t equals 0 plus SVC of S, like that. Now, don't forget, you've got all of semester 2 to get to grips with this. And one of the things I'm expecting you to do between now and when I see you next time is to go through all this mathematics and make sure you understand it. You've got to understand it before you sit that exam. You've got to be familiar with using Laplace transforms, doing inverse Laplace transforms, and carrying out Laplace transforms. You've got to be familiar with that. So, let's see what we do now then. Well, we could start off like we did before by saying let VC at time t equals 0 be 0, in which case that would be 0. So that's one possible initial condition. And that's what we'll do. We'll make VC at time t equals 0 equal to 0. Like I've said right at the very top here. At time t equals 0, VC equals 0. So this thing now becomes simplified. It becomes I as a function of S is VC as a function of S over R plus SC VC of S, like that. And we can rewrite this as VC of S into 1 upon R plus SC, like that. Or, what we can say is that VC of S equals I of S all over 1 upon R plus SC, like that. We can divide the top and bottom of that equation by C. You see that C there? Divide the top equation by C, the numerator, divide the denominator by C, and if you do that, you get IS over C divided by, divide the bottom by C, and you get S plus 1 upon RC, like that. Have you seen this formula before? Yeah. It's a familiar formula. But of course, we know I equals I naught equals a constant. We know that. And because we know that, what that implies is that I of S equals, someone guess? What's I of S equal to? If I naught over S, well done, good one. And we can just put that I naught over S into there. Just stick it into there. And so we can write down the final equation, which is VC of S equals, it's going to be I naught over C, 1 over S into S plus 1 upon RC, like that. And the reason why I put it in that form is because Carl has taken with him the Laplace transform tables, and I don't have them here. Ah, you've got Laplace transform tables. Carl hasn't taken with him the Laplace transform tables. I've got them here in my hand. And so we want to look through the Laplace transform tables and find something which helps us to inverse Laplace transform this. Now, of course, I naught over C is a constant. The capacitor's not changing. The constant current is the current source that we set it to. That's not changing. So that's just a constant. We've just got to say inverse Laplace transform 1 upon S into S plus 1 upon RC, and then multiply it by this constant here. And that will give us VC of T. And if you look in the Laplace transform tables, you'll get VC of T equals I naught over C, inverse Laplace transform this here, the 1 upon S into S plus 1 upon RC, and you find it's here somewhere there. You see that one? Let's go into it and look at it. That's a 1 upon S into S plus, and of course our A is 1 upon RC. That's what our A is. So we have 1 upon A into 1 minus e to the minus AT. That's what we have. But don't forget that A is 1 upon RC. Don't forget that. So we can write as A equals 1 upon RC. If you put A equal to 1 upon RC in here, put A equal to 1 upon RC in there, you get this equals RC into 1 minus e to the minus t over RC. That's what you get in there. And so we can do that here. We can do it here. And so what we will get here is 1 RC, like that, into 1 minus e to the minus t upon RC. And don't forget that once we've done that, go small again. So we're just using that Laplace transform. We cross that c with that c, and we get that happening. So that's what the voltage across the capacitor is going to do. It's going to do exactly what I've described there. And if I was to draw it, which is what I want you to be able to do, so I'm going to try and plot this expression now. So I'm going to plot this expression here. I'm going to try and plot that expression. I'm going to try and plot Vc as a function of time equals I naught R into 1 minus e to the minus t upon Rc. Well, of course, we know that I naught R. You see that I naught R there? That's got units of volts, just like this has got units of volts. So we know we're onto a winner here. We know that this is probably right, because resistance times current is volts. And this is just a number, isn't it? You've got 1 minus another number in here. So if you were to plot this now, Vc versus T, well, that's I naught R. I naught R. I naught R times 1 is just I naught R. At time t equals 0, anything to the power naught is 1. 1 minus 1 is 0, so it does this. Now we do have a rise, and the final value of the voltage across the capacitor, which is the same as the voltage across the resistor, is I naught R. In other words, all this current here, I naught, all this current here is now flowing through that resistor, like we described at the beginning, and no current is flowing through the capacitor, so the capacitor voltage stays fixed at the voltage across the resistor, which is I naught R. And so you get this behavior like this. Have you got any questions there? No? Great. That's fantastic. Do you all follow it? Do you need this to go on here like that so you can see it? Say again? Have we got any questions from anybody? Now, when it comes to the exam, you shouldn't be getting anything harder than we've done today. Now, you would have followed all the steps that we've done today. If not, you need to go and delve out my notes that I did in the second year in control, and you'll find that in those notes, all this stuff is in there. A lot of this stuff is in there as well. How you Laplace transform, how you inverse Laplace transform, how you set up an equation, how you then manipulate that equation, how you can manipulate it to get it into this form that we need to, so it looks like the Laplace transform tables. So you've got all of that. And don't forget, you've got all of semester 2 to get to this level of depth of understanding. So we've got quite a long time. But what it does mean that you've got to do in your own time, it means that you've got to work at this and go through it in your own time. Okay? What I want you to do now is write down this question I've got for you to do. I want you to submit to me when next time we meet. When next we meet, I want to see the solution. You should be able to do it on an A4 sheet. I've done quite big equations here, quite big symbols, but I'm guessing that when you do it in your homework, then it won't be as bad as that. So, this is the question I want you to do. Not looking too different yet. We've got that equation just by looking at it. In the exam you can't do that. I want every mathematical step shown on your exam paper. So what you've got to do is show how you get to that. We know what the answer is going to be. Show how you get to that. Let me ask a question of you. Put your hand up if you feel that you could confidently do every mathematical step to show how you will arrive at this equation here. Put your hand up. I can see 1, 2, 3. Anybody else? No one else. Just three of you. Do you want me to do it then? Yeah. Okay, I'll do it. Here we go. Ready? So what we have to do is we have to say IC equals C dvc by dt, because that's this expression here, that's what's going on. Now we Laplace transform it. Notice the big difference between the fact that I've got IC here and I as the current flowing around here. Two different symbols. We can Laplace transform this, and so if you Laplace transform it, you get IC of S equals C minus VC at time t equals 0 plus SVC of S. So that's step done. Now we've got to apply our understanding. What is the Laplace transform IC of S? We can write that IC of S equals, if you Laplace transform, well, we know that IC is equal to minus I naught, like that. We know that is the case. So we've got to Laplace transform minus I naught. So the Laplace transform of minus I naught is going to be minus I naught over S, because it's a constant over S when you Laplace transform it. And we've done the right hand side. Now we can equate these two. So we can say that that's equal to C into minus VC at time t equals 0 plus SVC of S, like that. Are we okay with that? But we know this. We know that plus VC at time t equals 0 equals minus V naught. Can you see that one? See where that one's come from? Plus VC at time t equals 0, the initial voltage on the capacitor at time t equals 0 is minus V naught. There it is, right at the top. At time t equals 0, VC equals minus V naught. Now that expression, you could actually write it as VC at time t equals 0 equals minus V naught, like that we could write it. And of course that's what we've got here. So all we have to do now is, instead of having minus VC at time t equals 0, like that, we've got to put in there instead minus V naught. We have to put minus V naught in there instead. Now, there's already a minus VC at time t equals 0. So if you put VC at time t equal to 0 as minus V naught, then the minus times a minus becomes a plus. Can you see that? The minus times the minus becomes a plus. And so you can write this line down now as minus I naught over S equals C times VC at time t equals 0. Plus V naught, like that. Like that. Because VC at time t equals 0 is minus V naught, there it is. Multiply it by the minus, it becomes plus V naught, and then you've got plus SC VC of S, like that. Now, we want to determine what VC of S is. That's what we want to find out. So what we have to do is bring this onto the other side. Bring that onto the other side. So what you have on the other side is, and we can write this on the right-hand side, if you write on the left-hand side, we can have SC VC of S, which is this over here, that, is equal to minus I naught over S minus C V naught, like that. I've taken it back over to this side. Can you see that? And now, of course, I can divide by SC, and divide by SC, so you get VC of S equals minus I naught over C, 1 upon S squared, minus CV naught, all over SC. That goes with that. And now I do the inverse Laplace transform, and I'm inverse Laplace transforming. Don't forget, that's all a constant. This is a constant. This is a constant. The V naught is a constant. The I naught over C is a constant. So you get VC of t, the inverse Laplace transform, is minus I naught over C times t minus V naught. And that equation is the same as this equation here at the top. That equation is the same as that equation at the top.
Zoom out.
That's doing all the mathematical steps. Now, of course, when it comes to the exam, okay, you will have the mathematical steps in there, but what you will also have is some words. You'll be putting some text in there as well. You won't just be putting mathematical expressions, you'll have text in there explaining what we're doing. So that as I mark it, I can understand what you're thinking before you get to the next line. I've missed all that out. And the reason why I've missed it out is because I've been doing this, and I've been talking rather than writing it. But you, when it comes to the exam, will write it, won't you? You'll write it. Great. I've got an exercise for you to do now. Does anybody want these sheets of paper I've got here? Is it helpful to anybody? To keep, yes. I don't want them. Well, if I give them all to you, then maybe you can do something with them. And I'm going to give you these as well. These are nice. These tables.
I might do. That's a worth to you.
Fine. What's the time, please? The time.
5 past.
Now, do you want a 5-minute break before we come back? Comfort break? Or yes? Get yourself a drink, have a break. You've had enough maths. I've been bombarding you with it all the time. You want no more right now. Then come straight down. 5 or 10 minutes. Come back.
What's this?
It's easy for you, isn't it?
It's like film.
Is it worth you while just making sure that
For your project?
you can get that appraisal form to me?
I think it's PCB boards.
Yes, made up. Yeah,
Right.
yeah.
How much is it?
I think it was £30 for 10. So it worked out right. It's a 2-week turnaround. I stuck on Facebook.
Did you do the routing for it?
No, I didn't do that.
Oh, you do the rules and they just print it.
Yeah, they just print out. They print out what they CAD
And the reason why that
drawing you give them
is
basically.
because they can't
CAD drawing.
Yeah, so like there's if you use multi-sim, if you use the Ultiboard, yeah, and then you get rid of like route it correctly, and then you just give it to them.
Yeah, I do know the
Like, how long does it take to write? 2 weeks.
So I've got two.
It's good.
Well, hopefully, if it works right, it should be okay. If it's all correct.
No, or maybe, no, I wrote the report while I was there, or I may have left the report to write, but that's different. Well, that's different.
Sounds a lot more than me.
Okay. Well,
I think actually there was some confusion over that. I'll speak to him again and get them back.
okay. All he has to do is reflect back on your abilities. Give him the form. I sent you a copy of the form, haven't I? Tick box. Yeah, the appraisal. It's a single A4 sheet. It will take you no more than 5 minutes to complete.
Yeah, well, I didn't see him, so
Yeah.
probably better.
Well, if you send him an email saying, look,
The email to you directly, did you get it?
I've not got it.
Was it CCB email?
Did it? Can you email it? Have you got it there? Let's see. Has it got attachments to it?
I went to my work address, to your university address, so I went to get access at that time.
You won't be able to access it. Well, shall we go to my office and see if we can access it? Now, find it.
There was just confusion over it. You split it up, so I like that.
Okay. Well, I've had a look at my emails, and if I'd have got it from him, I would have put it in my file for you. I've got a file for every person. Okay. So I've got your file, and when I open it up, yeah. When I open it up, I have some documents, but I don't have all the documents. So I need to get that from you. Yes, you can do that. On the specification, yeah. Did you not do any hardware?
No, I've done hardware.
Did you get the hardware for that?
No, I sent an email
Yeah.
to.
We can go to my office now if you like, and have a quick look. Yeah.
I sent an email for.
Yeah, come on. Yeah. Oh, you.
Do you have any specifications, or have you done it all through testing?
No, I just did it in the mouse.
Now don't forget, that's the initial condition, is that at time t equals 0, Vc equals V0 is a constant value. So you've got a voltage across that capacitor at time t equals 0 initially. That's what you have. That's what you have. And what's going on here is that this current here, I0, I equals I0 equals a constant, like that. And the question is what does VC do? That's the question. I want all the mathematical steps with all the text in between the mathematical steps explaining what you're doing. All the steps. Yeah.
So we have the next session next week, and we set after Easter now.
I don't think it is next week, according to, there isn't one next week. It gives you plenty of time to do this question, doesn't it? To get all the steps right.
Sure.
Make sure you can get all
Yeah,
those
because you've got
steps correct.
VC is equal to a voltage already, so it's not starting from 0 volts. The other one, last one was starting from 0 recently. Yeah, VC is equal to 0 last one, whereas VC is equal to V out.
It is. Someone's saying it's the same as the previous question. Is it the same as the previous question?
Similar.
It's similar. How is it different? What's different about this one?
We have a constant voltage at time equals 0.
That's it. You start off with some voltage on the capacitor. And what I want you to do, that I haven't done, is I want you to draw what the voltage on the capacitor is doing. So I want you to write, make sure you write that down. So I want you to plot or draw plot or draw the voltage across the capacitor as a function of time. That's what I want you to do.